integral tables. This is another method to evaluate integrals, and it's not one that we've run across so far. It's more of an old-fashioned way to do it, if I may say so, but I think it's worth acknowledging that this is something that is a legitimate strategy and it's worth knowing something about. Basically, what happens is that you have some integral that falls into some form, and there's these tables of pages and pages of integrals, and you can just match up your integral with the one in the table. So, for example, the one we're going to be looking at is the integral of square root of 9 minus 4x squared over x dx. And so there's a kind of pattern that we should see here. We've got 9, maybe you're thinking of that as like a squared, so there's like an x squared here, under a square root divided by x. So maybe we're thinking that we can do this with trig substitution, and that would probably work. But let me just show off. If we look at the very back of our textbook, the last couple of pages has this table of integrals. Now, lots of these are going to be easy ones that you know. I mean, you know that the antiderivative cosine u du is sine u plus c. That's right here. But then, you just have pages and pages of more complicated ones. And some of these over here, forms involving a square root of a squared minus u squared. Well, that looks kind of what we have. And so, trying to compare things says that number 69 in the table tells us that the antiderivative of the square root of a squared minus u squared du divided by u is equal to this expression right here. So we can pattern match. If we can rewrite this to look like this, we'll be all set. Okay, so first thing, this looks mostly like this, but the big difference here is that this is just a u squared here, this is a 4x squared here. So our first job should be to factor out a factor of 4. So the antiderivative of 9 minus 4x squared, we want to pull that's a x, not a u. So we want to move a 4 outside that square root. And that comes out, of course, as a square root of 4, which is 2, times the square root of 9 over 4 minus x squared divided by x dx. Okay, now we should be able to play a pattern matching game. So a squared here, a is going to be 3/2, because when we square 3/2, we come up with 9/4, minus u squared, that's just going to be minus x squared, divided by x dx. And so now, this looks exactly like this, and we're ready to apply this formula up here. So what do we end up with? It's going to be, 2 times the square root of a squared minus u squared minus a is, didn't I write that down? A is 3/2 minus 3/2 times the natural log of a 3/2 plus the square root of 3/2 squared minus x squared. All of that divided by u. U is x here. So there is our answer. Of course, we could replace the 3/2 squares with a 9 over 4. I want to do that to emphasize. I want to leave it in this form to emphasize where that's coming from. But here we have a relatively pain-free way to calculate out integrals. So obviously, going back to this, if you don't have a table integrals, then the best way to do it, and integration with a trigonometric substitution is certainly going to be a good way to tackle this problem. This would require, it looks like, the sign substitution. And it should be acknowledged that, like, probably doing a sign substitution is how this formula was developed in the first place. So yeah, an old-fashioned method, but one that's worth noting. Used to be, so the integral table in the back of our textbook has 3 pages. It used to be that you could just buy books with, dozens, if not hundreds of pages of integrals for you. Okay, that's the method of integral tables.